Morning, everybody. Good morning. If you can hear me in the back, raise your hand. Awesome. Good morning. Good morning. I like to see everybody conversing and interacting. That is why we meet in person. So good to see you all for day 2. Welcome to our Landscape Summit. Yesterday was an excellent day. I want to congratulate all the speakers for doing a very good job, staying on time. I was particularly impressed with the team talks. They all stayed on time very well. Usually those go off the rails just a little bit. So good job. Give yourselves a hand. I'd like to recognize there's many people that make this type of event a reality. And so I want to recognize in the front row, we've got our Zoom moderators, Madeline, Caitlin, and we have our timekeeper, Melissa, who some of you met yesterday if you were speaking. And so thank you all for keeping us on time, keeping the Zoom folks connected. This is by the way, I didn't say this yesterday, this is the first time we're doing a hybrid where people on Zoom, they see me, they hear the speakers, and it seems to be working pretty well. We've got a few people who could not make it for various reasons, or people that need to come in and out. So welcome Zoom participants, welcome to everybody here. And we will get started with day 2. We've got a couple different features today. We've got faculty lightning rounds. So these are 10-minute talks. So to give you just a kind of a flavor of what they are working on. And we do have some longer, what we think of as research talks later on in the morning. And then we've got the student poster competition. That'll be right before lunch. Each student will have 3 minutes. I think we're 3 minutes, right? Okay, 3 minutes and 2 slides. Okay, so we upped it. We doubled the amount of slides from the last time we did it. It was 1 slide and 2 minutes. And we got some feedback that people wanted more time. People always want more time. But 3 minutes to give your elevator speech in 2 slides. So stay tuned for that around lunchtime. And I think that's all I have. So thank you again. And I'll turn it over to our moderator, Cynthia. Thank you for moderating. And thank all of our moderators for agreeing or being voluntold or however they ended up being moderators. So thanks, everybody.
All right, welcome everybody to our second day of the 2022 Urban Landscape Summit. We're going to have some lightning rounds going on this morning. So I just wanted to, for the presenters and for everybody participating, to kind of know how that's going to work. So each presentation, it's 7 minutes. Our timer will provide a yellow light for those presenting. The yellow light will come on when you have 2 minutes left in your presentation. So at that kind of 5-minute mark. And then a red light will come on at the end of the 7 minutes. And then you have an additional 3 minutes for questions. You can go into that 3-minute time period if you need to, but then we will let you know when you need to wrap that up to be at your 10 minutes. So and also for the speakers today, remember if you have questions to just repeat that question for our Zoom audience. And I think that's all for the rules. Again, with the doors, remember that these doors, you can go out, but you won't be able to come in these front doors. If you need to come in, go out, come in the doors in the back. So without further ado, why don't we go ahead and get started on our first speaker, Dr. Mary Lusk. Why don't you come on up? Here you are. She's going to be giving a presentation on up in the air and down in the water, connections between the atmosphere and water quality in Tampa Bay. Thank you, Dr. Lusk.
Great, thank you. It is so good to be here with you in person, to be talking to everyone and seeing everyone. Really excited today to talk to you about a project that we started this year that we have called Up in the Air and Down in the Water, because what goes up comes down, right? So anything that goes up into our atmosphere very likely can come back down and make its way into our water bodies. So I'm going to give you a quick overview of this project today. You are undoubtedly aware of watersheds. Water bodies also have air sheds. This is the Tampa Bay airshed. So air masses from all of that area in the circle there can make their way to the Tampa Bay area and contribute rainfall to the Tampa Bay estuarine waters. So we can get it coming from over the Gulf of Mexico or across the Atlantic or up from Cuba and the Bahamas, or it can come down from the Atlanta area, or those air masses can originate right there in the Tampa urban area. And depending on where those air masses come from, they're going to bring a very different type of load of potential pollutants in the rainfall that falls over the Tampa Bay. So all of these air masses carry with them some nitrogen. If any of you have ever seen any talk that I've given before, you know that I like to point out about atmospheric nitrogen. I love studying it and thinking about it. So that atmospheric nitrogen in all of those air masses can come from various things like manure emissions or forest fires or just lightning. We have a lot of that in the Tampa area. We lead the world in lightning strikes, or fossil fuel burning, so vehicles and fossil fuel plants. A recent study done in 2013, that's the most recent data that we have, that was done by the Tampa Bay Estuary Program, found that 57% of the annual nitrogen load to the Tampa Bay Estuary comes from atmospheric nitrogen. So 17% of that is just direct rainfall on the bay waters, and 40% of that is indirect loading from stormwater runoff from the Tampa Bay watershed. But it combines to bring 57% of total nitrogen, which is greater than any other source of nitrogen to our Tampa Bay waters, including fertilizers or wastewater treatment or whatever the case may be. A lot of nitrogen. This has been very understudied. This study that was done in 2013 has really been about the only one that's looked at that until now. And so this is a little conceptual diagram that we put together to kind of help visualize what's going on. How are we getting that 40% per year of total nitrogen load from the Tampa urban watershed into Tampa Bay via atmospheric deposition? So again, those air masses can come from a marine source or from over land. So we've got two different types of air masses there at the top. They're both bringing down rain. Pathway 1, of course, is just that rainfall falling into the urban area. Pathway 2, that rainfall interacts with the urban tree canopy. So trees intercept some of the water, but trees may also augment that rainfall with nutrients because there's a lot of nitrogen and phosphorus on those tree leaves. So we've got two processes going on there in the urban tree canopy. Process number 3 is just that bulk precipitation that's converted to runoff because it falls on impervious surfaces. And pathway 4 being then that runoff making its way to a surface water body. So those processes right there, 1 through 4, contribute about 1,300 tons of nitrogen to the Tampa Bay estuary every year. That's that 40% of indirect atmospheric deposition to the bay. So this is what we want to study. We want to hone in on these processes 1 through 4 and really do a deep dive on that in the Tampa Bay area. So this work is being done by my PhD student, Amanda Mooney Morgan, who is not here with us today. But in a nutshell, she has identified a bunch of research sites in Pinellas County in the Tampa Bay area. She has research sites on both sides of Pinellas County, on the Gulf of Mexico side and the Tampa Bay side. And she is looking at doing 3 years of storm event sampling of bulk precipitation or just rainfall, stormwater runoff, and through fall from the urban tree canopy. So through fall is just that rainfall that's interacted with the urban tree canopy. She is analyzing that for just nitrogen forms and concentrations, the molecular characterization of organic N. So a lot of that nitrogen is in organic compounds that we have never characterized before. So she will look at the specific chemical characterization of those compounds, optical properties of that. We're also going to do storm backtracking, so we can tell, did this storm come from the Gulf of Mexico or did it come from Atlanta? Because we hypothesize that where it comes from will play a large role in the nitrogen character of that storm. And then she's also incubating these water sources with Carenia brevis and Pyridinium bahamis, which are 2 of the harmful algal bloom species that we see in the Tampa Bay area. So in a nutshell, she's basically just taking that 1 through 4 process and she's following the water through that process and looking at it. Also, we had some help from Paula Sanchez Garzon, undergraduate in our lab this year. So I wanted to share some quick data that she collected in this project this year. So she had a 21-acre urban catchment with about 57% impervious cover. She was collecting the throughfall, the stormwater runoff, and the bulk precipitation rainfall at the same event in time. So same time, simultaneous sampling, very close spatially to each other. You can see under the tree, we're collecting throughfall. Over on the other side, we're getting the open rainfall. So very close spatially to each other. And we're comparing nitrogen in those types of water. All I have for purposes of time today, I'm going to show you dissolved organic nitrogen in those waters. This is on the x-axis by date. Y-axis is total dissolved organic nitrogen concentration. Look at how much throughfall was enriched with nitrogen, really enriched, because as it interacts with that tree canopy, rainfall is picking up nitrogen. When we convert those to fluxes on an annual basis from this little small study that Paula did, you can see here the different forms of nitrogen and rainfall and throughfall, and how the throughfall is enriching those different forms of nitrogen on an aerial basis every year. So for example, total dissolved nitrogen, which is the last one in that table, the rainfall is giving us about 9 kilograms per hectare per year of nitrogen, but the throughfall almost 23 kilograms per hectare per year of total nitrogen. Again, because of this picture right here, all the things that are in that tree that can be picking up nitrogen as the rainfall falls through it. We also looked at optical properties of this, and big thanks to Audrey Geckner, a PhD student who helped with this. We collected a lot of optical data on this storm, but I'm just going to show you this one for time. This is the Humidification Index, and you can again just see the big difference in how that water qualitatively changes as it moves from rainfall to stormwater to throughfall in humidification. So the higher the number of that humidification index, the more that organic nature of that water sample is more high molecular weight, very aromatic organic compounds. And we're definitely changing qualitatively the nature of that organic nitrogen as we move through those watershed components of rainfall, stormwater, and throughfall. Last slide here, just a conceptual diagram to help sum it up and help you see what's everything that's going on here. So think about it in a natural ecosystem, nitrogen in that rainfall and that throughfall is processed by watershed soils, right? Just like on the left side there. But on the right side in our urban environments, we bypass watershed soils. So we don't have that processing of that material anymore. And it can just make its way to our coastal water bodies. Some summary points there. Trees in our study site, we estimated they're avoiding or capturing about 20,000 gallons of stormwater runoff every year. So that tree is definitely giving us a net benefit of capturing some of that stormwater flow, but it's also augmenting the nutrient load by concentrating that throughfall. So you can see the numbers there for you. So my last point of this is just a plea for pervious surfaces, a plea for green infrastructure, and a plea for green space under our urban trees because of how much that throughfall can concentrate and augment those nutrient loads underneath the trees so that we don't end up with the situation on the right. So instead we can have the situation on the left. Okay, so thank you. That's my enlightening round.
We have about a minute and a half for questions.
Okay, AJ.
This is awesome. Really cool stuff, Mary. I'm glad that somebody is doing the whole mass balance on this finally. Like I know you're following you and others. Great. I was really interested by the throughfall changing the composition of the nitrogen. So you're getting an increase in DON concentration, but it's seemingly less labile, probably less bioavailable. And then also when you scale it up, like the total flux is higher on a per hectare basis. But I was wondering if when you scaled up those fluxes, did you account for the reduction in the actual precipitation making its way to the ground and then also the relative surface area of canopy in the area?
We did. So that's a great question, AJ. And to repeat his question, he wants to know if when we upscaled that, when we looked at fluxes on an aerial basis, do we account for the uptake that the trees are doing just to uptake water volume. So we've got two things going on here. We've got Q, water volume, and we've got concentration, the concentration of those nutrients. And short answer, no, we did not. But longer answer, that's in the works because we definitely want to try to model that a little bit and account for both of those so that we could say, what is the net benefit of the trees on this site? We're getting the benefit of stormwater uptake, but that's being offset a little bit by the throughfall concentration. So we want to model that and look at that a little bit better. So yeah.
That's all the time we have, unfortunately. That's what happens with these lightning rounds. We got to keep moving. But thank you.